Hello, this is Professor Katroulis. There had been a request in my Chemistry 140 discussion online to go ahead and post some information about millimoles and BCA tables, and I know there were also some problems with ion concentration, so I wanted to hit those topics kind of quickly here. So let's start off by just talking about the concentration of ions. So let's consider for a moment any compound which is a strong electrolyte in water. So if something is a strong electrolyte, what does that mean? Well, you'll recall that the definition of strong electrolyte was it's a compound which completely dissociates into ions in solution. And we have three major categories of strong electrolytes. They are the strong acids, the strong bases, and soluble ionic compounds. Technically, the strong bases are soluble ionic compounds, so we could almost say that there are really only two groups. The strong acids, the five that I think are clearest to understand, are hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and then sulfuric acid, but all of those two protons, we call this a diprotic acid. We'll talk more about this in chapter 14. But of those two protons, only the first proton or hydrogen ion readily comes off. But if this is put in the contact of a strong base, both hydrogens will be pulled off. So in water, only one is lost. But as I said, with a strong base, you lose both. The strong bases are essentially all of the soluble hydroxides. So this will definitely include the group 1 hydroxides, such as sodium hydroxide, potassium hydroxide, lithium hydroxide, and although I'm not going to write them here, rubidium hydroxide and cesium hydroxide. Also, barium hydroxide, although it is much less soluble than the group 1 hydroxides. In other words, you can get less of it to dissolve and dissociate in water. And then we have strontium hydroxide, same thing, not nearly as soluble. And one which is somewhat controversial would be calcium hydroxide. Some people would argue that's not even soluble enough to be considered a strong base. Soluble ionic compounds, anything which, if you follow the solubility rules, are soluble. So for example, anything which contains ammonium ion, anything which contains a group 1 ion, let's see here, what else? Essentially all acetates. So if you go ahead and go through the list that you learned in Chem 130, you'll recall those lists, or even in Chem 120 for that matter. Now I'm mostly interested here in the ions which dissociate completely to form multiple ions. So for example, let's take a look at magnesium bromide. In water. What that essentially means is that in water there is a magnesium ion dissolved, and because of the presence of this 2, that tells us that there should be 2 bromide ions dissolved as well. There might be slightly less than 2. That's something that we get into in Chapter 11. But for right now, we're just going to assume that this is an ideal case and all of those ions completely break down. Same idea, say, for example, with barium hydroxide. In water, that's a barium ion, which is dissociated in addition to 2 hydroxide ions. So what this means is that if we know the molarity of either of these compounds, say magnesium bromide or barium hydroxide, the molarity of the ion will be the coefficient of that ion times the molarity of this compound. So for example, if I had 0.10 molar magnesium bromide, that would mean essentially the same thing, that my magnesium concentration, assuming no other source of magnesium, would be, well, what's the coefficient of magnesium? It's 1. I didn't write it down, but it would be 1 times the molarity of magnesium bromide, because every 1 mole of magnesium bromide gives me 1 mole of magnesium ions, and so that would mean that the molarity is simply the same for the ion as it is for the solution. However, for the bromide ion, because there are 2 bromide ions for every 1 magnesium bromide unit in the dissociation process, that means that we're going to get 2 of those for every 1 mole. So the molarity would effectively be doubled. Oops. There we go. For that in solution. Looking at barium hydroxide, so if we had let's say 80 molar barium hydroxide, well, when barium hydroxide dissociates, you get 1 barium for every 2 hydroxides. So that would mean that the barium concentration would be the same as the barium hydroxide concentration. However, the hydroxide concentration would be double that, because there are 2 hydroxide ions for every unit of barium hydroxide in water. With sulfuric acid, the case is complicated. So, for example, if I had 1 molar sulfuric acid, if I go to look for the proton concentration, well, what am I going to know about it? Let me rewrite that. Well, it turns out that, as I said, the first proton comes off very easily. So that means the proton concentration is going to be at least 1.0 molar. However, only some of the protons are lost, and how much is actually lost is a topic for Chapter 14. But even if you lost both, it would have to be less than or equal to 2.0 molar. So for right now, we cannot say this. We cannot say that we know the concentration of the proton, because we simply haven't learned how to handle that. It's definitely at least 1 molar, though. But, and this is the important thing that I want to bring up, as I mentioned a moment ago, if sulfuric acid is placed in the presence of a strong base, the base will pull off both of those protons very, very easily. And so even though in water it turns out that sulfuric acid might not completely dissociate both protons in base, strong base, both of those hydrogens will definitely be pulled off. And even in weak base, a substantial proportion of them will be pulled off. So that fact will come up a little bit later when we're looking at BCA tables. And the important thing to understand about this is that for every sulfuric acid, when it reacts with a strong base, you lose two protons right here. Okay, so really the only thing to do there is you look at the formulas that you get when a compound dissociates, a strong electrolyte, and you simply multiply those by the coefficients to get the ion concentration. Next, I want to talk about millimoles. I find that students initially find millimoles confusing, and for me this is always a mystery, because if anything, they make your life much, much easier in solution chemistry. And so we symbolize these with mmol. Milli means the same thing that it always meant. Milli simply means 1,000th, which is 10 to the minus 3. So if a mole is 6.02, 2 times 10 to the 23rd of something, then a millimole is simply 1,000th of that. So let me be clear here. 10 to the minus 3 is the same thing as 0.001. So that's just 6.022 times 10 to the 20. That is the definition of what a millimole is, but it's essentially a useless definition. We're not going to really need to use this at all. And let me explain why we would be interested in using the millimole. First of all, whenever we're dealing with small quantities, the millimole is much better to use than using moles. And this is particularly the case when we're dealing with anything involving solutions where you're using less than 1 liter. Now, we all know that the equipment in our lab for measuring volume, virtually all of it is in milliliters. None of it is in liters. And so since we're going to be working mostly in milliliters, it's going to make more sense, as you will see, to work in millimoles instead of moles for most of the time. So let's look at the most common things that we need in terms of measurements here, and that is we often need to know how many moles of something we have. And the way that we figure out moles of something is typically by mass or by volume of a solution, assuming that our compound is dissolved in solution. So this is assuming we know the molarity. Okay. So how do we get back and forth between mass of something and moles? We use its molecular weight, or we'll say molar mass. And to get between moles of a solute, so I'm being very specific here, solute, to volume of the solute, or excuse me, volume of the solution, we use molarity. Now let's look at the definition of each of these. So molarity. This is just the theory. You'll never need to apply this theory. Again, it's just to explain why this next convenience will work the way it is. So the molarity is defined as we've already seen, moles of solute for every liter of solution. SOL'(N) is the abbreviation. Now, as you should already know, we can multiply both the numerator and the denominator by the same number, and that does not change the value. In other words, I could multiply the numerator here by 1 over 1,000, and I could multiply the denominator by 1 over 1,000. And since 1 over 1,000 divided by 1 over 1,000 is 1, I'm not changing anything here. So what this means then is, what is 1 over 1,000? Well, as I just mentioned a second ago, that is milli. So I can come up here with an alternative definition of molarity as, let's just do this with color for a second, millimoles of solute for every milliliter of solution. Now, to be clear, we could do this for any of the metric units that we wanted. We could have kilomoles, and the molarity would then be kilomoles over kiloliters. We could use micro and have micromoles over microliters. All it's doing is just working at different levels of scale. And since we are mostly going to be working with milliliters, this scale is going to be much more useful for us in most cases. Let's do the same thing with molar mass. So molar mass is defined as the grams of a substance, so generally a compound or an element, for every mole of that substance. I can do the exact same trick. Let's just say I want 1,000th of a gram for every 1,000th of a mole. You agree that multiplying by 1,000th over 1,000th is the same as multiplying by 1. So that doesn't change the value of the molar mass at all. So this would mean 1,000th of a gram would be a milligram of solute for every millimole of substance. Now, to be clear, these millis can be canceled out just like you can cancel out units or you can cancel out equal values. Because as I've said a couple times here, milli simply means 1,000th. So those two m's right on top of each other can cancel and just give you back moles over liters. So that means that these are exactly the same values. So in other words, if I see 0.80 molar sodium chloride, then that means either 0.80 moles of sodium chloride for every liter of the solution, or, and it also means, I'm writing or, but probably should write and here, 0.80 millimoles of sodium chloride for every milliliter of the solution. Now you're going to see that the advantage of doing it this way is that you're not going to have to convert molarities to liters if you're using millimoles instead. And so that takes a step off the beginning of most problems and a step off of the end for titration problems, as well as a lot of the ion concentration problems as well. So that will, as I said, make things generally more convenient for us. Now, it is also true that if we have a balanced equation, so for example here, hydrochloric acid plus sodium hydroxide makes water and sodium chloride. So the ratio here is 1 to 1. So we know that if I read this, I can read this as 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide. So let me write that down. So 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide. Since this is a 1-to-1 proportion, I could pick any number, like 2 moles with 2 moles or 5 moles with 5 moles. I could say 1,000th of a mole of hydrochloric acid reacts with 1,000th of a mole of sodium hydroxide. And we just said 1,000th of a mole is a millimole. So 1 millimole of hydrochloric acid reacts with 1 millimole of sodium hydroxide. So you see, if we're trying to do the stoichiometry part and looking at how things react with one another, it's no different working in moles than working in millimoles. The coefficients work exactly the same way, no difference at all. The only times you really have to be careful with millimoles is if you're going from millimoles to grams. As we saw up here, you can't directly go from millimoles to grams. You have to go from millimoles to milligrams. But then going from milligrams to grams is very easy. You just divide by 1,000 and you now have the value in grams. Okay, now let me explain why this is really useful. It is really useful because to find the millimoles of a solute, you simply multiply the volume in milliliters by the molarity. So, for example, if I have 40.0 milliliters of 0.50 molar HCl, all I have to do to find the millimoles of HCl is just multiply those numbers together. And 40 times 0.5 is simply 20 millimoles of HCl. That was just so easy. Let's do another one. Let's say I had 15 milliliters of 1.50 molar sodium hydroxide. And I want to know how many moles or millimoles that there are. I believe 15 times 15 is 225. Let me just check that. Yeah, 225. So this is 15 times 1.50. That's a tenth of that. So that's just 22.5 millimoles. So the really nice advantage here is, number one, to get to millimoles of something, it's so easy to do if you know the volume and the molarity. It's just a multiplication problem. And the answers that you get are very nice answers typically. 22.5. Nothing that needs scientific notation or lots of zeros in the decimal number. It really makes life easy. Let me just prove why that's the case, why it's just a multiplication problem. So if I had 40 milliliters of the hydrochloric acid solution, we know that the definition of the molarity in terms of millimoles is for every 1 milliliter of the hydrochloric acid solution, there is 0.50 millimoles of hydrochloric acid. Remember, this is just the molarity. 0.050 moles of HCl over 1 liter. All I chose to do was put 1,000th over 1,000th in it. So nothing has been changed. So you see, it's just a multiplication problem. And that's exactly where we ended up getting the answer here. Why do I need to do that? Well, remember, when we're talking about reactions, and we want to know how many grams of something reacts with how many grams of something else, or what volume of a solution reacts with volumes of another solution, it's not molarity that we want, it's moles, because things react in a mole ratio. So by the same concept, it makes sense that it would be much easier to work with millimoles here. Like, for example, if I want to figure out if these two react, I want to know how much of which reactant is left over. This is super easy to do in our head. We know that HCl gives us 1 proton, sodium hydroxide gives us 1 hydroxide, and that they react 1 to 1. So there's more sodium hydroxide than HCl. So all of the hydrochloric acid will be consumed. We lose 20 millimoles of it. And of the 22.5, we would lose 20 millimoles of it. It would form water. And you'd be left with 2.5 millimoles of hydroxide. And what the volume would be, well, we don't know unless, well, actually we do, because we've got the volumes right here. So I would be left with 2.5 millimoles of hydroxide floating around in 55 milliliters. And I could easily find the molarity of that. That would be 2.5 millimoles divided by 55 milliliters, or 0.0455 molar sodium hydroxide solution. So you see, it's very fast, very simple, and much easier once you know what you're doing than going through the standard calculations. However, because I'm sure many people couldn't follow that in their head, and I totally understand that, you don't have the advantage of doing this for, well over 20 years, we're going to see that there is an even easier way to systematize this, and that is by using what we call BCA tables, or before, change, after. And I'm going to go ahead and leave that to another video on its own. So I'm going to go ahead and end this video here. I hope this has been instructive, and if you have any questions, feel free to contact me by email at mkatroulis@riohondo.edu. Thank you.